Thank you everyone for joining us today. I have the pleasure of introducing Carolina Casadio. Carolina was a former student of the University of Bologna. She graduated here with Professor Giovannini and myself a few years ago. And then she moved to Spain, to Granada, the Instituto de Astrofísica de Andalucía, for her doctoral studies in the group of Professor Gomez to study VLBI, so Very Long Baseline Interferometry data of relativistic jets in polarimetry. After the PhD, she moved to Germany, to the Max Planck Institute for Radio Astronomy, for a postdoc position in which the challenge raised because she moved to millimeter VLBI, which is quite challenging. And after she completed her experience in Germany, she moved to Crete in 2020 in the group of Professor Vasiliki Pavlidou, and she joined the Institute of Astrophysics there. Just a few months ago, she was awarded an ERC starting grant for a project called SMILE on the topic of lensing. And that's what she's going to talk to us today. And so the floor is yours, Carolina, and thanks again, everyone, for being here.
Thanks. Thank you very much, Marcello. Thanks for inviting me. Can you confirm that you can see my screen?
Yes.
Thanks. Okay, so hi, everyone. I'm very glad and very happy to be here today because, yes, as Marcello said, I've been the SMILE project, this project has recently awarded an ERC starting grant. So this kind of a new start for me, and I'm glad to give a seminar here in Bologna where my career, my passion for radio astronomy starts thanks to Marcello, Gabriele, and many people there. So I will talk about, so the SMILE project will officially start actually in July. So what I will talk you today is about a pilot study that we performed to support this project. And obviously as well also about what is this project about. Here you have listed the name of my collaborators, the SMILE team. So the name of the project is SMILE, that stands for Search for Milli-Lenses, because in this project we use the gravitational lensing on the key but poorly explored milliarcsecond scales to search for supermassive compact objects, as for example dark matter halos at sub-galactic scale, as I will show you along the talk. So let me start with this plot that tells us how few we know about our universe, because roughly the 95% of the total energy content of the universe is made of unknown forms of energy and matter. And in the standard cosmological model, this matter is in the form of cold dark matter particles, which are non-relativistic at their origin and they are collisionless. But because of the elusive detections of these particles from one side and because of the difficulties in explaining all possible scales in the universe by the lambda CDM model on the other side, then there are still many viable dark matter models nowadays on the table of discussion. And many of these dark matter models have been created exactly to solve lambda CDM paradigm issues. Here I listed only some of them. This is not the dark matter model review. Probably the most well-known, the most famous in literature, which are the self-interacting dark matter models where cold dark matter particles scatter elastically between each other. Then we have a cold dark matter model with ultralight dark matter particles, so the fuzzy cold dark matter. And then we also have the well-known warm dark matter model where particles are semi-relativistic at their origin. But dark matter doesn't have to be necessarily a particle. There are in fact also non-particle candidates, as for example, primordial black holes. The range of possible masses for this object is quite wide because this reflects the different formation time at the very early stage of the universe for this object. And there was recently a renewed interest associated in this object associated to the detection of the gravitational wave event 1905-21 that was associated with a merging between two black holes where the primary black hole has a mass of around 85 solar masses, which falls within this mass gap for stellar origin. So as I said before, the lambda CDM model is quite successful in predicting the formation of the large scale structures in our universe, but it still has some issues, mostly at galactic and subgalactic scales. At subgalactic scales, for example, it predicts a number of dark matter halos, which is far above the observed number. And also, in this case, at subgalactic scales, the density profiles of these dark matter halos seem to differ from the predicted ones. And this is exactly what we have in this plot here, where you have you have the density profiles of a large number of dwarf galaxies from this Little Things survey published in O et al. 2015 that are represented by the green points. And as you can see, these green points are rising more slowly toward the center of the halo than the gray curves that instead are the called dark matter Navarro-Franken-White density profiles that predict the formation of a high density cusp-like center in these dark matter halos. While instead of these the density profiles of these dwarf galaxies seems to point to the formation of a core-like center. And because of this problem is usually referred as the core cusp problem. But it is exactly at these subgalactic scales where different dark matter models make very different prediction on the expected number of dark matter halos. This plot is showing you the power spectrum of baryonic acoustic oscillation for different masses and different scales. And the gray shade area is highlighting exactly these subgalactic scales. If you focus on the blue curves that represent different dark matter models, the solid line is the cold dark matter model, then the dashed line is the warm dark matter model. And you can see that the warm dark matter model has a cutoff around 10 to the 8 solar masses, which means that if the warm dark matter model is the right one, then we should see in the universe structures with masses below these around 10 to the 8 solar masses. So you understand from this plot how important it is to estimate the number of dark matter halos at subgalactic scales, because this may tell us to what is the nature of the dark matter. And so if constraining this number is so important, then why this number hasn't been tightened, hasn't been constrained yet? So basically because these dark matter halos at subgalactic scales, they are very hard to be detected. So here on the right, you have an image images of dwarf galaxies spanning 6 orders of magnitude in stellar masses, from the most massive and most luminous ones at the upper left to the less luminous and less massive ones at the bottom right. These last one are only detectable in a small volume around the Milky Way. So you already see from this picture, from this photo here, how difficult it is to detect these dark matter halos, at this case, using optical observations. So, and this is because being smaller and being more dark matter dominated, they are extremely faint. And this applies to those dark matter halos that at least form galaxies, because below in some in 10 to the 8 solar masses, they are not even expected to form galaxies. Therefore, they are dark. And then the only way we have to detect them is through the gravitational effect that they exert on ordinary matter, therefore using gravitational lensing. But in order for a dark matter halo to make strong lensing on a background source, it needs to have a surface mass density above a certain threshold. We can parameterize, let's say, this density with this parameter here, that is the concentration parameter, that tells us how basically concentrated toward the center is the mass in a dark matter halo. So in this recent study, Wong and collaborators investigated the concentration of a large number of simulated dark matter halos of different masses versus their masses. That is exactly what you have in this plot here. And one of the main results is this one, is that dark matter halos at sub-galactic scales that are delimited by this orange line here are far more concentrated than, for example, the galaxy cluster dark matter halos that are instead limited here by this gray line. So, and since we know that galaxy cluster as well also as galactic halos make strong lensing on sources in the background, then we can argue that also at least the cores of these dark matter halos at subgalactic scales should be able should be dense enough in order to make strong lensing on background sources. And so since these dark matter halos at subgalactic scales, then they are so highly concentrated, and they are also, they have small masses, then we can approximate them with a point mass lens. And we know from the gravitational lensing theory that the point mass lens split the image of the source in the background into two lensed images whose angular separation, if the source and the lens are at cosmological distances and for order of magnitude precision, this angular separation depends only on the mass of the lens. Therefore, if the lens is a compact object with a mass between roughly 10 to the 6 and 10 to the 9 solar masses, I will call from now on this object a supermassive compact object. Then we expect the angular separation between the lensed images being in the milliarcsecond regime. And for this reason, we call this gravitational lensing system MIlli-LEnses. So then you understand that the direct observable of MIlli-lensing are supermassive compact objects with a surface mass density above a certain threshold. That is the one you have here, as I mentioned before. Astrophysical objects that can satisfy this condition are, for example, as I just mentioned, the cores of subgalactic dark matter halos that we can find associated to galactic halos or even free floating in the field. But there are also other astrophysical objects that can satisfy this condition, as for example, supermassive black holes at the center of galaxies, as the one that we find in active galaxies, or even primordial black holes that, as I mentioned before, are considered a major component of the dark matter by some dark matter models. Until now, the search for this object, for dark matter halos at subgalactic scales, has been addressed mostly using what I will call indirect observational methods. And I will explain you later why I call them like that. So one of them is this one. So it makes use of gravitational lensing, but this time at galactic scales. So the lens this time is a galaxy with its own dark matter halo. And in this case, we can have two different scenarios. So in the case where the source in the background is an extended source, as for example, another galaxy, or for example, a radio loud quasar with a resolved jet, then we can have the formation of arc-like structures, and in some cases, even the formation of an entire Einstein ring, as in the scenario A. In the other scenario, is the source instead in the background is a compact source, as it could be, for example, a galaxy observed at optical frequencies, or a radio compact quasar. And in this case, we have instead the formation of multiple compact component lensed images, as we have in this scenario B. In any case, in both cases, since in gravitational lensing, we know that both the magnifications and the position of the lensed images depend of the lens mass distribution, then any anomaly on these physical quantities may reflect the presence, for example, of an extra mass condensate that participated to the gravitational potential of the lens. And this is how this method works. Then we have another method that is instead basically use the density perturbation of in stellar streams in the Milky Way, where these stellar streams are stars that are escaping disrupting globular clusters. And again, when these stellar streams encounter a mass condensate, there can be a density perturbation. But in this case, you understand that it's very difficult to know if this density perturbation was something intrinsic to this stellar stream or given by a gravitational lensing event. Then the last method is still making use of gravitational lensing, but in the time domain. So using lens gamma ray burst. And with this method, in principle, it's possible to reach up to smaller masses for the lens than not in the two previous methods. Like in this event here, in this paper of Verens and collaborator 2021, they use the GRB 210812A, and they using the flux ratio and the time delay between the two events of this GRB, they were able to estimate the mass of the lens that they found to be a lens of roughly 10 to the 6 solar masses. So as I said before, all these methods are, I call them indirect observational methods because it's very difficult to understand and to know if what you are observing is something intrinsic or is given by a gravitational lensing event. And so if you want a more direct proof, then basically you need of the presence of this mass condensate, then you need to have the images produced by this supermassive compact object. And since as I told you before, we expect the lensed images having an angular separation of the order of the milliarcsecond, then we need the milliarcsecond resolution. And the most direct way nowadays to reach this very high resolution is using the very long baseline interferometric technique. So in this technique, basically, many antennas located in different places around the world observed together and effectively using the entire Earth's surface as if it was one unique antenna. So here you have the two main VLBI arrays in the northern hemisphere that are the one I'm interested in, which are the European VLBI Network with antennas located in Europe, in Asia, and one in South Africa. And the VLBA with antennas instead located mostly in the North America. So then we perform a pilot search for this type of objects. In this pilot search, we use the publicly available data from the Astrogeo VLBI FITS image database. You have the link here. This database contains data mostly coming from astrometry program devoted to the completion of a radio fundamental catalog. And for this reason, most of the sources are compact radio sources that are observed at multiple epochs and multiple frequencies. And so at the time we performed this search, we collected the data of almost 14,000 sources. We perform a stacking of images for those sources where multiple epochs were available. And then we finally create a web page to visualize all these images. And then based on the idea of the science, of the citizen science project, we involved 5 PhD scientists and 9 undergraduate physics students from the University of Crete in the search. And people were asked basically to mark as a milli-lens candidates those sources that have multiple compact components at milli-arcsecond scales in at least one observing band. And then to possibly mark instead as a non-candidate, non-milli-lens candidate, instead of those sources that were clearly displaying a core jet-like feature structure, as the example in the right here. Then, because the people involved were not expert in gravitational lensing nor in the agent physics, then we also insert as a sort of quality check in the sample to be visualized. We also insert 200 mock lenses, where these mock lenses were creating basically, as you see here at the bottom, just faking the emission of a secondary compact component and placing it in different places within the field of view of the image. And so at the end of this first step of the visual inspection, we found that of the 200 mock lenses, 8 of them were missed. But fortunately, 6 of them were missed by two persons in particular. So then we reinspected the roughly 1,000 sources inspected by these 2 persons. And we were able then to finally assess a final loss rate of 1%. And plus, we also found 4 more lens candidates. Then we performed 2 more steps in this visual inspection. This time instead involving also people expert in either gravitational lensing or agent physics. And we ended up at the end of these different steps of visual inspection, we ended up with a total of 59 candidates. Then as a last step, we filter out sources based on the surface brightness preservation criterion. So gravitational lensing is an achromatic effect that preserves some physical quantities, and one of them is the surface brightness of the lensed images, and which means that a secondary weaker component is also smaller than the primary brighter component. And so we use an apparent surface brightness ratio lower than 7 then to obtain the final list of the 40 best milli-lens candidates. And we published this this list in this recent letter appear in monthly notice. So here you have also an example of the images of these 40 milli-lens candidates that you can find in the Astrogeo image database. And just as a reminder, so all these sources have multiple compact component at milliarc scales in at least one observing band. And plus the putative lensed images, they also have an apparent surface brightness ratio between components lower than 7. Then based on the on spectral index measurements, we also suggested the two most probable milli-lens candidate, which means that these sources have two compact components with a similar and flat spectral indexes. So the fact that they are similar is important again because, as I mentioned before, gravitational lensing preserves some physical quantities between the lensed images. And these are this one. So the surface brightness, the flux density ratio at the same frequency among epochs, and the flux density ratio between different frequencies that translate into the spectral index. Moreover, the light rays producing the two lensed images have different paths, and this introduces a time delay between the lensed images. But since this time delay depends on the angular separation of the lensed images, and in milli-lensing we are dealing with very small angular separation, then this means that in milli-lensing, the expected time delays are very small. Usually they are some tenths of second or some hours. So, and this is very important because this tells us that the time delays in milli-lensing are not affecting either flux density ratio measurements nor spectral index measurements. However, in the case of spectral index measurements, we cannot discard the possibility that the light rays in their two different paths are crossing different media with different absorption coefficients, which will lead then to different spectral indexes for the different lensed images. And for this reason, we use the spectral indexes of the putative lensed images just as a suggestion and not as another constraint to filter out sources. Then also the fact that they are flat is important. So here you have a famous gravitational lens system at galactic scales. So here the lens is a galaxy G1 plus another dwarf galaxy nearby, G2. And they are splitting the image of a radio compact quasar in the background into these four images that you find here. And since we know that the bulk of the emission in this radio compact quasar comes from the core, and the cores usually have flat spectra, then we expect the spectra of these the spectral indexes of these lensed images to be similar, but not only that, we also expect them to be flat, as it's exactly the case. It is exactly the case for this gravitational lens system here. And if this, for example, can help us in distinguishing between a milli-lens system and other type of sources that can have a similar morphology similar to what we expect in case of milli-lenses, but they are something different, as for example in this case where you have again two compact components, but one is the core and another one is a secondary component along the jet, and in this case they have different spectral indexes, and usually the secondary component has a steeper spectral indexes than not the core. But let's say that in general, these are the steps that we need to follow in order to confirm a milli-lens system that we are doing now for this pilot study, but that we will also do obviously for the more extended project. So we need to inspect the VLBI images in search for these sources with multiple compact components on mass scales. Then we need to discard sources that are not passing this surface brightness preservation criterion. And then once we have more information in our hand, we can also proceed in measuring the physical quantities that I was mentioning before. So the spectral indexes between the components, flux density ratios within epoch, and so on and so forth. So in order to collect more data for our pilot study, then we asked and obtained new EVN time for the follow-up of our 40 best milli-lens candidates that we performed with the EVN at 5 and 22 gigahertz. And then basically once we have this new follow-up observation in our hand, we will proceed doing the same type of search, because we first of all have to confirm that in the new epoch, the source still has the same type of morphology, because these sources are extremely variable. So it's possible also that they are not passing even the first test anymore. Then basically sources that pass all these tests will be tested against lens models to see if the flux density ratios and also the lens images positions are in agreement with a lens model. And then this will be the last, obviously, test to reject or to prove the milli-lens system. So if basically we will find any milli-lens system, this will be a big and major discovery, because no milli-lens system has been found yet. But in case we don't find any, obviously these sources are not for trashing. They are still very interesting sources, because of their morphology, they can still be investigated as either compact symmetric objects or even supermassive binary black hole candidates. So CSO are considered the young counterparts of the nowadays extended radio galaxy, large radio galaxies. And in this object, the bulk of the emission comes from these lobes, that is where the terminating jets are interacting with the interstellar medium. And in most of these objects, the emission of the central engine that is expected to be in between of these two lobes is obscured. And for this reason, their morphology resemble very much what we expect in case of a milli-lens system. And instead here on the right, you have a multi-frequency VLBI images of the only morphologically confirmed supermassive binary black hole system. And this is interesting because based on the fact that we expect that most of the galaxies have at their centers supermassive black holes, and based on the hierarchical formation of galaxies through mergers, then we would expect to see many more of them, but this is not the case. So then, as I mentioned before, we ask and obtain for new EVN follow-up observation that we perform at 5 and 22 gigahertz in phase referencing, for a total of 140 hours that were split into 5 observing sessions. The analysis of this data is still undergoing, so I will just show you some preliminary results on some sources. So this source J0527 plus 1743 In the new EVN 5 GHz image, we confirm its morphology, so the presence of these two compact feature at the mass scales. The source still passes the surface brightness preservation criterion in this new image. But when we measure instead the flux density ratios of between the two putative lensed images at the closest frequencies, then we find some discrepancies. So this means that most probably this is not a milli-lens system, but obviously we will also investigate further the source also with the addition of the 22 GHz.
10 minutes, Carolina.
Yes, thanks. So then this is a second source, J0237 plus 1116 instead is in the new image is not showing anymore these two compact feature. And we think that here what plays a role is most probably the variability of this source, that in this new EVN 5 GHz observation shows what it seems a more typical core jet-like structure, while maybe in the Astrogeo epoch was maybe ejecting a new component from the core, and this was the secondary compact component. And this core jet scenario is also supported by the astrometric position of the optical emission as given by Gaia, which is closer to the core and not in between the two compact components as we would expect in case of a milli-lens system. Then a third interesting source is this one, J1143 plus 1134, that we detected at both 5 GHz and 22 GHz. We detected the emission from both compact features. And in case this source is at the end will be discarded as a milli-lens system, it's still a very interesting source because it was previously defined as both CSO and the supermassive black hole, binary black hole candidate by previous studies. So then in this, in the SMILE project, we plan to perform the same type of search, but on a complete sample of almost 5,000 radio loud sources, again using VLBI observations, but this time taking care of data from scratch. And a radio astronomer in the audience easily understand the bulk of the load of work behind this project, because we want to obtain high fidelity images. It's very important at the end. I will show you. It's very important to be able to properly constrain the number of milli-lenses. So the idea behind this project comes from these two pioneering studies. So from Press and Gunn first in 1973 developed the idea that the number of gravitational lensing events by supermassive compact objects directly probes the mass density, therefore the abundance of these supermassive compact objects in the universe. And then later on, Wilkinson et al. In 2001 uses this idea to constrain the abundance of supermassive compact objects with masses between 10 to the 6 and 10 to the 8 solar masses, using a sample of 300 sources and VLBI data. And this is here, and it's the constraint that they obtain with no milli-lens system found. With the SMILE project instead, we will constrain the abundance of supermassive compact objects with masses between roughly 10 to the 6 and 10 to the 9 solar masses, with more than an order of magnitude better precision than in Wilkinson et al. 2001. What you have in this plot here is the density of the universe locked up in objects of a certain mass versus that mass. And as you can see, the constraint that we will obtain with our project will be below the lambda CDM prediction and an order of magnitude better than the one from Wilkinson et al. 2001. So since the goal of our project is to constrain the abundance of supermassive compact objects in the universe with roughly 16 times better precision than in previous studies, then we need to have a sample that is roughly 16 times larger than the one in previous studies. And then to do so, we basically use the original class catalog, where class is the most successful to date search for gravitational lens system at galactic scales using radio frequencies. So we use the original complete class sample that has this characteristic listed here. And we selected the sources with a total flux density at 8 gigahertz from VLA observation higher than 50 millijansky. And we ended up with roughly this number of sources, 5,000 of sources. Then since we want a new VLBI observation for these all these sources, we cross-match the SMILE sample with the data in the NRAO archive, and we found that roughly 75% of our sources have data there. And so then we went to and we asked and obtained new observations for the remaining 25% of sources.
And you have 5 minutes left. Yes,
I'm almost done. So then the direct observable of the SMILE project will be the abundance, as I just said, of these supermassive compact objects in the universe. But since we are interested in a particular type of supermassive compact objects that are these sub-galactic dark matter halos, then we want to know what is the number of this object that we expect to detect through milli-lensing. And this number depends on both the density profile of dark matter halos as well as on the mass function of dark matter halos, which in turn depends on the dark matter particle properties. And it also depends obviously on the experiment that mostly depends on the size of the sample. And as I said before, SMILE will have the largest sample ever for this type of search. So then to compute this number, so what the number that we expect, the expected number of dark matter subgalactic halos that we expect to detect through milli-lensing, we computed this quantity here, the optical depth for each one of the source in our sample, where the optical depth is the probability that a source has a source that is placed at a certain redshift has to be lensed by an object in the way. And this, so since this quantity here depends on the redshift, then we have redshift information for almost 2/3 of the sources in our sample. And for the remaining 1/3 of sources, we assume a similar redshift distribution. Then this quantity here also depends on the number density of the lens population, that in this case are these subgalactic dark matter halos, that, as I said before, then this number here depends on the density profile and the mass function of dark matter halos. So this parameter here is the one that is changing for different dark matter models. Then we have the lensing, it depends on the lensing cross section, which in turn depends on the length of the mass of the lens and the redshift of the lens and the source. And then we have this, that is the length, the path length, that in turn depends on the cosmology used and on the redshift of the source. So then once we have computed this optical depth for all the sources in our sample, we basically sum up all these quantities, and we obtain the expected number of dark matter halos that we are able to detect through milli-lensing. And this is what you have here and what we computed. So if the warm dark matter model is the correct one, we don't expect to have any milli-lens system just because of that cutoff around the 10 to the 8 solar masses that I was mentioning at the beginning of the presentation. Then we computed this number also for 3 cold dark matter models, which have different dark matter, which has different, density profiles, where two of them have density profiles that come from n-body simulations and theoretical predictions that are this one. And one of them instead, in one of them we use a density profile that we derived from observation of galaxy cluster. What I want you to focus here is on the different number that we have for different dark matter models. That is basically telling us that the SMILE project will allow us to robustly discard some of the viable dark matter models. While this was not possible basically in the past, for example, in the study of Wilkinson and collaborator in 2001, just because of the size of the sample used in that study. If instead, in fact, so since the sources in the two studies have a similar redshift distribution, we can use this formula here to basically infer the same expected number for the study in Wilkinson et al. In comparison with the number that we obtained for the SMILE project. And this is this formula here at the bottom. So if you apply this formula here to the different cold dark matter models, you have 0 for all of them, which means that basically just because of the size of the sample size, the study in Wilkinson et al. 2001 was not able to discern between these different dark matter models, while SMILE will be able to do so. And now basically I finish. So I just want briefly I will leave you here my last slide. I just want to advertise the opening soon of 2 postdoctoral researcher and 2 PhD student position here that will be held here in Forth in Crete. And so if you are in love with radio astronomy, if you like reducing VLBI data, and if you have enjoyed listening to this about this SMILE project, so then please contact me here. You can contact me, and you will find more information at these 2 web pages. So yeah, I'm done. Thanks.
Thank you, Carolina. Thank you, and again, congratulations for the nice project and the ERC grant. And I encourage, of course, everyone to contact you about these positions. Okay, time for questions and comments from the audience. You can open your mic, raise your hand, or write in the chat. Christiana has raised her hand. Please, Christiana.
Thanks, Carolina. It was super nice talk, nice results. So mine are just 2 curiosities. Maybe I missed that, in case, sorry for that. So in slide 26, you show your the limits that you can put on how much you can push down the limits of Wilkinson. But I was wondering, what is the uncertainty on that limit? Because I saw the bar, and I was wondering if you have also an error bar on the y-axis on that.
Yes.
Yes, this one here.
This one here, right?
Yes, exactly.
Yeah. In this one, so it's so the error bar basically is just the number that I show you at the very end. So that is the most correct expected number that we computed at the end, basically. So here was just an approximate, let's say, computation, because here we even assume, to be fair here, that the mass of the lens is equal to the mass of the halo.
Okay.
That is so.
Okay.
So this was just a preliminary, basically, computation to see how how much below, so how better in sensitivity. But this was a preliminary estimate. Obviously, we have to introduce the density profile to have better estimate, and this was done for the latest calculation.
Okay, thanks. That sounds good. And another is just a curiosity, because you know that we did something similar using the MJIVE survey.
Yes.
And did you find any quadruple imaged candidates or only double imaged candidates? Because we haven't found any quad.
No, you mean for the pilot study,
For
right?
the pilot, yeah.
No.
Okay, and I find it interesting, but yeah, that was a curiosity. Thanks a lot.
Yeah.
Okay, any more questions or comments? I have a question on the science part and one more curiosity. So about the science, you know that the class was also used as a base for Crete to look for counterparts of Fermi gamma ray sources, and also the RFC, the Astrogeo database, is dominated by bladas, which are also gamma ray sources. So I was wondering if you plan to include also a study of the high energy properties, because Fermi gives you like the light curve, and so you could use that to look for signatures in the time domain rather than in the image domain. And the other question I'll ask later because I see a raised hand.
Okay, yes, that's an interesting point. Yes, that will be very interesting. Also, again, it's in the time domain. So the time delays, as I said, in milli-lensing, you expect time delays very, very short, right? It can be from tenths of seconds to hours. So I don't know about this. The very short, let's say end of this range, if we can say something.
Yeah, it's more for the GRB side.
Yeah, exactly.
Those are not in class. Okay, thanks, Carolina. Filippo has a raised hand, so please go ahead.
Yes. Hi, Carolina. Very nice talk. Very interesting results. I have a question. We have developed a new way to select in the optical compact lensed quasars with separation between 150 mass to up to 400 mass. So sub-arcsecond separation, but above 100 milliarcseconds. Can this be of any use for your project, or separation are too large, so you only sample above the cutoff, the expected cutoff?
So, the angular separation, if the lens is this supermassive compact object, then the angular separation we expect it to be lower. So it's a maximum something like 150 milliarcsecond or something like that for 10 to the 9 solar masses, more or less. So in that case, the lens is usually a galaxy, not we are dealing with bigger objects. What I think there I mean, the technique used there in the case of when the lens is a galaxy is the one that I was mentioning before, right? So you can still use these gravitational lensing images, explore them, and see if you have any anomalies in the physical quantities of these lensed images. So like flux density ratios, spectral indexes, or so on, and that may be hint for the presence of an extra
inside the lens galaxies.
Exactly,
okay.
Exactly. The good thing I think of this project is that we are probably okay. In principle, it's also with this. In the case you are mentioning, this mass condensate could be placed anywhere in between the source and us, but usually is the most probable that is in the surrounding of the galactic halo. While instead with this type of search, we are kind of blind, and we are also probing about the existence of this mass condensate free floating in the field. Just as an extra
Thank you.
information.
Carlo?
Carolina, thank you. Very nice talk. So I wanted to ask you a question. So what is the idea for if you have a positive lens system? What is the idea to model and to have some constraint on the projected matter density distribution of those lenses? Mm-hmm.
So how are you asking me how we are going to proceed once we have a milli-lens candidates, right?
Yeah, which is confirmed.
Yeah, I mean, yeah, in order to confirm it, so since there are no milli-lens system confirmed or observed yet, I think that we will start triggering whatever type of observation if we have a very good candidate to get any possible information on the lens, first of all. So it's at other wavelengths, right? To see if we are dealing with dark matter halos or other type of object that still can do milli-lensing, like supermassive black holes, for example, that can be either at the center of galaxies or wandering in a galaxy. So we first have to go for follow-up observation at whatever frequencies to understanding which type of scenario we are, to collect as much information as possible. And I think we can easily get observation, because again, since no milli-lens system have been found yet, it's going to be very interesting science case. And then once we understand, if we can understand from follow-up observation what type of lens we are dealing with, then we will have more information to perform any lens modeling. I think this is a plan.
Thank you.
Okay, thanks. I don't see any more raised hands or comments in chat, so I'm going to ask my final curiosity, and then we can close this event. And the curiosity is about your original approach based on citizen science rather than, for example, machine learning. Is there any reason why you chose to do this, or you regret having not done anything different?
No, not at all. It was it was nice. It was fun also, to be fair, to go over and visually selecting sources. And we are planning also to continue on that. But we are also thinking about, we are exploring other type of approach also for the future, like machine learning, but it's not that easy. But we are exploring also some more automated approach. Yeah.
Okay, thanks. Okay, I think we can close the talk for today, and I would like to thank Carolina again and congratulate again for her grant. Best of luck to her and her group. Please give my best to Vaso and everyone there. And thanks everyone for participating, and we'll see you next week.
Bye.
Thank you. Bye-bye.
Bye-bye.
Bye.
Thank you. Thank you. Bye.
Ciao, grazie. Ciao.
Ciao. Ciao, grazie a voi.
Ciao.
Ciao, grazie.
Ok. Grazie Carolina, bellissima, che lavoraccio.
Sì. No, è stata interessante anche quella del Citizen Science Project. Credo che sia servita. Non abbiamo avuto con queste anche mock lenses che abbiamo inserito un po' per vedere se le persone stavano attente, se avevano capito che cosa fare.
Che dormivano, no? Sì, sì.
Esatto, non gli avete fatto due pasticcioni che le ha sbagliate tutte.
Purtroppo. Però esatto, per fortuna ne abbiamo avuto solo 2, quindi è stato veramente un buon risultato in realtà, secondo me. Quindi non abbiamo dovuto rianalizzare più di tanto e secondo me, insomma, non è stato male, è stata una cosa interessante.
Va bene, mi ricordi un'altra cosa al volo? Le osservazioni VLBA a che frequenze sono?
Quelle di Astrogeo?
No, quelle VLBA, quelle nuove.
Ah, i VN.
99 ore. No.
Ah, no, scusa, quelle... Ah, sono con il nuovo C-band receiver.
Ok, quindi fate da 4 a 8.
4 e 7, sì, 7.3.
Okay. Ottimo, ok. Va bene. Dai, Carolina, senti, è stato un grande piacere. Facci sapere quando vieni ad aprile. Salutami tanto Vaso, mi raccomando, che non la sento da una vita, ma lo voglio tanto bene. E quindi ti prego di farlo, insomma.
Volentieri. Adesso quando iniziamo questo progetto anche siete benvenuti qua, se volete venirci a fare un saluto. Crete è bella, quindi...
guarda.
Vabbè, sì.
Piacerebbe tanto.
Volentieri.
Dai, va bene, grazie ancora.
Va bene.
Va bene, vi scrivo. Ciao, grazie.
Ciao,
Ciao.
Carolina, ciao.